Okay, lesson 5.2 is titled Independent and Dependent Events. It's on page 47 of your guided notes. We're going to split this into two videos. The learning target here says students will be able to distinguish between independent and dependent events. We're going to talk about what that means and then calculate their probabilities. To start out with, we're going to talk a little bit about conditional probability and how we calculate that. And then we'll talk more specifically about what happens if more than one event occurs, or we want to find the probability of more than one thing happening. We call it joint probability. So, first of all, conditional probability. Our definition right here says this is a probability that takes into account a given condition. Okay? Given two events, that should say events, A and B, the conditional probability of A given, and that's the key word in conditional probability, B, is the probability A occurs given B has already occurred. The conditional probability is written as, and you'll see this symbol down here, that bar between them. That bar represents given. So when you see it, we read it as A given B. We're finding the probability of A, and B has already occurred. Okay. For example, when being dealt a card from a standard deck, given the dealer has already dealt a heart to the player at your right, the probability of your being dealt a heart, given that a heart has already been dealt, means we must take into account that one heart has been removed from the deck. Okay, that outcome of the event is already fixed. Now, it's crucial when we're looking at conditional probability with that word given that we understand if the events are independent or dependent. Independent means they don't affect each other's outcome. For example, here it says find the probability of flipping heads on a coin given you are wearing purple. Now, whether you're wearing purple or not, there are only two sides on that coin, and the fact that I'm wearing purple doesn't affect how it lands. So the probability is still 1/2, even with this given, and that's because these are what we call independent events. They don't affect each other's outcomes. If they're dependent, then the outcome of the first will affect the other, just like we talked about with that deck of cards. The formula for conditional probability, when you see that word given, and again, maybe let's label that down here. This means given. And again, you're finding the probability of A, and then B has already occurred. Okay, so when we do that, what we do, and I'll show you how to use the formula and then why I kind of go through the formula. But essentially what we're looking at is the probability that A and B happen, and then we divide it by the probability of just B, or the probability that's already occurred, and that gives us the accurate probability. So let me show you how to use the formula, and then how we also can use kind of intuition in relation to the formula. So you draw a card at random from a standard deck of cards for this next example. Find each of the following probabilities. So part A says the card is a heart given that it is red. So I'm going to practice using the notation. Find the probability it's a heart given it's a red card. Okay. Now notice if I use the formula, that would be on the top, the probability of both events occurring. So the probability that they're red and they're hearts. Now all the hearts in the deck are red. So that would be 13 out of 52. All of those hearts are red. Then on the bottom, the probability that B occurs. So if you look at B, B is red. The probability you draw a red from the deck, well, half of them are red. So that's 26 out of 52. Remember when you divide fractions, I'm going to write the top one. So 13 over 52 divided by 26 over 52 is the same as flipping that second fraction and multiplying. When we do that, you'll notice that this denominator and this numerator are going to cancel, leaving us with 13 over 26. Or we can even simplify that down to 1/2, or write it as 0.5 or 50%. Now, we can use that formula every single time, but this is what you'll find is those denominators, right, are going to cancel every single time. So instead of thinking about the and thinking about the probability of B, a lot of times I just think about, okay, well, how many reds are in the deck, right? You're just considering a new total. It's given that it's a red card. So if it's given that it's red and there's 26 reds, it would make sense that 26 would go on the bottom. And on the top, we're calculating this out of those 26. Remember, now it's given you're in the red cards. How many of those reds are hearts? Well, half of them are, right? 13 of them are, so 13 out of 26. So using that same idea, let's jump to this one. Again, this means given. So this is the part that's already occurred, which is why I always put it on the bottom. That's my new restriction for my all possible outcomes. So it says, what's the probability it's red, given it's a heart? So if you think about it, there's 13 hearts in the deck. And then we say, well, how many of those are red? Well, all 13 hearts are red, so actually the probability is a sure thing. The probability it's red, given you're drawing from hearts, is a sure thing. The next one, the card is an ace, given that it is a spade. So I'm going to write this one out. What's the probability we draw an ace, given it's a spade? So again, if I'm calculating this, I think about, well, how many spades are actually in the deck if it's given that it's a spade? Well, that's one of the suits, so there's 13 of them. And of those 13, again, you can't leave those 13, how many aces are there? So every suit has one of each number, right? So there's only one of them, or 1 out of 13. D, probability it's a queen, given it's a face card. So again, I think about my deck and I think about how many face cards there are. There's a jack, queen, and king in every suit, so 3 times the 4 suits is 12. Of those 12, now you can't leave those 12 because that's the denominator. How many of those are queens? Well, 1 from each suit is a queen, so 4 over 12, right? Or in other words, 1/3. Okay, so again, the given just restricts our possible outcome there. And then of that given, we think about what's the probability we end up with that. All right, let's try it from a two-way table. Same idea again, but now we just have to refer to the two-way table. So notice up here, it says that we can find the probability here by finding the values where they intersect. So that's like the and then finding the total for B. So if a person in this town is selected at random, it looks like we have a table full of different age groups here, and then the type of employment they fulfill based on their age group. So we want to, on part A, calculate the probability the individual is unemployed. So again, I'm going to write it out because it helps me make sense of exactly what I'm looking for. I come up to the table, and this doesn't say given, so this is not conditional. We're just calculating the probability the individual is unemployed. So if I look up here at my unemployed column, right, this many individuals were unemployed, 823. So that would be 823 out of the total 3,179. Now, can I write that as a decimal? Can I simplify it? Absolutely. You can write it in any of the forms that you would like to. We'll just approximate it as a decimal for now. Okay. B, if a person in this town is selected at random, find the probability the individual is unemployed given, so there's that word given, that he or she is between the ages of 35 and 49. So as I calculate this, again, I'm going to write it out. So again, we're looking for the probability they're unemployed, but this is given that they're between the ages 35 to 49. So as I calculate, I can't consider anyone except those that are in the ages of 35 to 49. So if we look up at our table here, 35 to 49 is this row right here. So it's given we're in this row. So I'm going to put this over 864. And of those 864, how many are unemployed? So we look over here, we get 104 of them are unemployed, so we have 104 on top. C, we're given in probability notation, so calculate the probability they work full-time, given they're over 50 years old. So again, if I was doing this, I would look at, well, how many are actually over 50 years old? Because that's what's given. So if I look up here, over 50 years old, there's 778 of them. And of those ones, it looks like 443 of them work full-time. So 443 out of the total 778, I believe, is approximately 0.569. Lastly, on this one, calculate the probability they're between the ages of 18 and 25, given they work part-time. So if we look at this one, instead of a row, we're given that they work part-time, so they have to come out of this part-time data. So it's given they work part-time, so I'm going to put the total part-time on the bottom. Out of those 775, we want to know if it would be an 18 to 25-year-old, so I'll put 203 on the top. Okay, so again, the given restricts that total value you're drawing from. All right, last little bit, and then we'll stop this video and start the next. This says Miss K's class was surveyed to see if they have an iPod, cell phone, or both. The results are represented in the diagram. So find the probability the student has an iPod given they have a cell phone. So again, I'm going to write this out. iPod given they have a cell phone. Now remember, the given restricts you to a part of the data. So in a Venn diagram, it's going to be parts of the sets. So the probability they have an iPod given they have a cell phone. So they have a cell phone. So I'm going to come over here. Notice this circle represents students with cell phones. Once you're in this circle, because it's given, you're not going to leave this circle. Does that make sense? I'm going to release my pen. It's going to go away as a laser, but we're not leaving that circle. So that means 10 plus 15 is 25 there on the bottom. Of those 25, because we know they have a cell phone, how many have iPods? It would be that 10 there in the middle, right? So we could simplify that or write it as a decimal. The next one, find the probability they have a cell phone given they have an iPod. So again, we start with how many have iPods. And so we start in this circle this time, and we never leave this circle. So there's 14 in here that have iPods. Of those 14, how many also have cell phones? That would be that 10 again there in the middle. Ooh, that was a 1 and then a 4. All right, lastly, Miss K finds an iPod after class. What's the probability the owner has an iPod and no cell phone? So if we're thinking about this one, what's the probability? They have an iPod, but no cell phone. So we don't know, but it's given that they are going to have an iPod. If they have an iPod, again, we're in that same circle, and no cell phone would be these 4 out here. So we're given they have an iPod, only 4 of them. I apologize. They were given they have an iPod, 4 of them don't have a cell phone. So we are going to calculate that. Cool.